Hello gentlemen, and welcome to today's topic on Introduction to Thermochemistry. This is really the beginning of our new unit on thermochemistry. Thermochemistry is really a focus on thermo, heat, and obviously chemistry. We're really going to focus on sort of the science of thermodynamics. And again, thermo comes from heat. And dynamics is change or movement. Okay, so we're really focusing now in our chemical reactions, which we talked about in grade 11. We're going to take that and we're really going to study about how energy, heat, light move across and through it in a chemical reaction or a chemical equation. A couple things that we need to understand and define before we get started. First is energy, which is just known as the capacity to do work. In your notes, you'll find you have a blank version of this. Anything that it's in red, you're going to want to add. I would suggest writing it. You're going to remember it a lot better that way. So energy, again, the capacity to do work. Work is a force acting across a distance. Okay, so how much force you need to move something. So energy now is how easily something is moved, or how hard it is to move something across a distance. We deal with a lot of different forms of energy and classify them certainly in any situation, but in chemistry specifically, as potential and kinetic energy. Potential energy really is mostly due to a position or arrangement. Okay, it's associated with the attraction and repulsion between objects. Really, it's potential because of this arrangement or its position. We were kind of measuring how much kinetic energy or the energy of motion it's going to have. Okay, so potential energy, a little bit harder to sort of understand, but really it's all about position. It's about how much energy could this produce at any point. Kinetic energy, we can define that as K, and it equals just 1/2 of mass times velocity squared. So it's really two things involved in the energy of motion: how much something weighs and how quickly it's moving. So again, m is mass, v is velocity. Okay. When we combine the potential and kinetic energy in a particular substance, we get thermal energy. Really, and again, thermal, we're talking about heat energy here. Okay. When we discuss thermal energy, we have to consider the difference between heat and temperature. Heat, which we symbolize using Q, so the symbol for that is Q, is the transfer of thermal energy as a result of a temperature difference. Okay, so for example, you have a cold pack. Your hand is warm, the cold pack is cold. The energy from your hand, that thermal energy, that heat energy, transfers from your hand to the cold pack, warming that cold pack up over time. And your hand, as a result, starts to feel cooler because it loses that heat energy. Temperature, really, that's the measure of the average molecular kinetic energy of a substance. So if you remember back to grade 11, we talked about temperature. It's how quickly something's moving. Okay, the molecules are moving. Well, again, kinetic energy, that's that energy of movement. So on average, how quickly are those molecules moving? How much energy are they producing in that substance? Okay. This section we're going to leave blank. We're going to do a demo in class, so we're going to come back to that soon. So specifically in chemistry, we're concerned with changes in energy that occur during chemical and physical processes. Okay, so remember, chemical, physical changes. The chemical change, we've talked many times throughout your chemistry studies about the signs of a chemical change. But really the key thing here is, are you creating a new chemical substance? Or physical, where you just usually a change of state, or you're moving something, but not a new substance created. Okay, but really, when these two things are happening, either a chemical or physical change happen, if you have constant pressure, these changes can be observed in one of two ways. Either heat is released or absorbed, or light is released or absorbed. Okay, so I'm not going to give you any specific examples. Well, maybe I'll give you some examples. So for example, Something that releases heat would be a combustion reaction. And actually this falls into both. Combustion reaction, when you're burning something, light, heat is produced. Okay? The absorption of light, absorption of heat, the opposite. Okay? So when you're again, that cold pack, it's cold, but it's absorbing heat. Over time it starts to warm from your hand. When you cook something, same idea. Okay? Here you've got the absorption of light would be your skin from the sun. Again, releases light as combustion. Releases heat, again combustion. And the absorption of heat would be the ice pack. Okay, we'll see we'll talk many examples of these in class as well. The thing that drives this process is the first law of thermodynamics. And this states, it's also called the law of conservation of energy, but it's the idea that energy cannot be created or destroyed. So it has to come from somewhere. Even when you think about fire burning, there's potential energy in the log, and then there's kinetic energy that sort of kickstarts that fire when you spark it. Okay? There's no new energy being created there. The energy from that potential energy from the log is being changed into kinetic energy. Okay, again, the positioning of those molecules in the log, as they heat up, start to move more and more quickly, creating that energy as light and heat. Okay? So before we actually consider some chemical reactions, we have to consider how energy is transferred. When we take the law of thermodynamics into consideration, we realize that energy has to be transferred from one place to another. Okay, so just like I said, but in here now we're going to use two new terms, the system and the surroundings. How is this energy being transferred? So, your system, first of all, is the portion of the universe selected for that thermodynamic study, and the surroundings are the portion of the universe that encloses that system. So we think back to our combustion reaction. The system, okay, is if we had sort of an enclosed space you're burning your fire. Okay, surroundings are everything around it that might be affected by that. Okay, so now you're transitioning. Your log is your system, and the air around it might be the surroundings. So how is energy now transferred from that log to the surroundings? Well, you're heating it up. Molecules start to move more quickly. You're transferring heat energy to the surroundings. Okay, so when we talk about that, we need to classify these chemical reactions. And the first is reactions that result in a transfer of energy from the system to the surroundings. Okay, we consider those exothermic reactions. Okay, that release of heat or light. And reactions that result in a transfer of energy from the surroundings to the system, so the opposite way. So again, your ice pack example, consider those endothermic. Okay, so again, you're warming up the system using the surroundings. Now, we've talked combustion of butane. We're talking combustion. So you're burning butane, which is C4H10, with oxygen, creating carbon dioxide and water. How is the thermal energy transferred? How would you classify that? And where should we put the energy into the equation? So combustion, pretty straightforward. This I'm going to leave. And you guys are going to see this pop up in the Edpuzzle as a question. On another side of things, we look at the reaction between ammonium thiocyanate and octahydrate. Ammonium thiocyanate, octahydrate, and barium hydroxide. So in this situation, I'll show you the video. You're going to see what he's done is there's a thin layer of water below this beaker. You add the ammonium thiocyanate to the barium hydroxide octahydrate, and you swirl. Okay, so he's stirring, and I'm going to skip ahead because he stirs for a while. Okay. So after a while of stirring, the transfer of energy is occurring. Okay, so now your system is your ammonium thiocyanate and barium octahydrate. As that reaction occurs, the heat from the surroundings, so the water underneath, is transferred into your system. And we get this freezing of the block to the beaker. So again, the surroundings in this case have lost all that heat and have been transferred to the system. So in this case, thermal energy is transferred from surroundings to the system. We would then classify this as endothermic. And energy, in this case, should then go on the left side of the equation. So we can also classify the overall systems in 3 different ways, as being open, closed, or isolated. Okay, so if you remember the system, this is really where the reaction is happening. If both energy and matter can exchange with the surroundings, you have an open system. So as an example, if you look at my log burning outside, both matter and energy can exchange in a situation like that. There's no barrier there that's full. A closed system is one that can exchange energy but not matter with its surroundings. So a closed system, basically now you have a sealed container, maybe your beaker that's been sealed, right? Energy can exchange, as we saw in the video. There's heat energy going from the surroundings to the system, but matter cannot. Okay, it's in a sealed container, so a little bit different than the one that we saw. An isolated system is totally isolated in every way. So neither matter nor energy can be exchanged. So now you're dealing with a sealed, and it's going to be insulated as well. Okay, so this would be sealed container. This would be sealed and insulated. Thank you, gentlemen. See you in class.